But as an aside, when can you diagonalize a matrix? When can you diagonalize a matrix? Yeah, if the matrix is real symmetric, you are guaranteed you can diagonalize it. In fact, you can diagonalize it by an orthogonal transformation. But what is the general case? When can you diagonalize an n by n matrix? This is a problem in linear algebra. It has nothing to do with this course, but it is good to get. Yes, indeed, indeed, yes. So, well, here is a simple sufficiency condition. It is not necessary, but a sufficiency condition. If you have a matrix A and its Hermitian conjugate A dagger, by that I mean take its complex conjugate and transpose, it is called the Hermitian conjugate of the matrix. If A commutes with A dagger, which means that A dagger equal to A dagger A, by the way this stands for complex conjugate transpose. The Hermitian conjugate of this matrix, if it commutes with its Hermitian conjugate, namely if A dagger is equal to A dagger A, does not matter in which order you multiply it, this is called commutation. This is sufficient to ensure that you can diagonalize A by a similarity transformation. By that I mean you can find a matrix S such that SA S inverse is equal to the diagonal matrix. It is sufficient, it is not necessary. You would also like to have a sufficient and necessary condition. Well, you know that every matrix obeys a polynomial equation, its own characteristic equation. This is called the Cayley-Hamilton theorem. So if you write down determinant of lambda I minus A equal to 0, you get an algebraic equation whose solutions form the set of eigenvalues of the matrix A. And this equation looks like, in general, if this is an n by n matrix, it looks like lambda to the power n plus A1 lambda to the n minus 1 plus A2 lambda to the n minus 2 plus An equal to 0. That is the secular equation. In general, this is what it looks like, and the constants A1, A2, A3 are determined from the elements of the matrix A. Okay. And the Cayley-Hamilton theorem says that the matrix A itself satisfies this equation. In other words, you are guaranteed that A to the n plus A1 A to the n minus 1 plus An I equal to 0, and this is the Cayley The statement is every matrix satisfies its own characteristic equation. But of course there is nothing to stop the matrix from satisfying another algebraic equation, polynomial equation of a lower degree. This could well happen, that the matrix satisfies an equation of a degree lower than n, and the lowest such equation, polynomial equation, is called the minimal polynomial of this matrix. The lowest degree polynomial equation, that polynomial equal to 0, that is called the minimal polynomial. And a sufficient, necessary and sufficient condition that A can be diagonalized by a similarity transformation is that the roots of the minimal polynomial should be simple roots. There are many ways of saying this. One of them has to do with the rank of the matrix, which was mentioned indirectly here, but this is the necessary and sufficient condition. We will try to use it a little later, but let me give you an example here. Suppose you have a matrix, n by n matrix, all of whose elements are 1 1 1 1, everything is 1, and that is an n by n matrix. What are the eigenvalues of this matrix? Zero is certainly an eigenvalue because the determinant of this matrix is obviously 0. What happens if you do this? This is just playing with this matrices, but what happens if you apply it to this column vector 1 1 1? What do you get? You get n times the same column vector. n times the same column vector, right. So won't you say n is an eigenvalue? N is an eigenvalue and all the other eigenvalues are 0, every other eigenvalue is 0, because if you took this matrix its determinant is 0, if you took the first minor that is also 0, so you hit one of these columns and rows and the rest of it also has 0 determinant, and that keeps going till you hit this element itself, and that is not 0. So all the minors are 0 and therefore this matrix has 0 eigenvalues, n minus 1 of them, the last one is n. So this matrix has lambda 1 equal to 0, lambda 2 equal to 0, lambda n minus 1 equal to 0, just one of them. So it is easy to write down the characteristic equation of this matrix. It is immediately obvious from here what the characteristic equation is. So it says a to the power n minus 1, a minus n, that is the characteristic equation of this matrix. It is an nth order polynomial equation and it guarantees that n minus 1 roots are 0 and one root is n. Instead of a you replace it by lambda and that immediately follows. But this is not the minimal polynomial of this matrix. What is the minimal polynomial of this matrix? What is the lowest order equation that this matrix satisfies? What do you think is the lowest order equation? Well, it cannot be a linear equation because a is not equal to a constant, a is not the identity matrix. So it can't be alpha a plus beta I equal to 0, it can't be an equation of this kind. The quadratic, what happens if you square this matrix A? Na, a squared is Na, so we know that a squared minus. So the minimal polynomial is in fact a quadratic in this case. What are the roots of the minimal polynomial? 0 and n, 0 and n. Are they simple roots? Yes. So you are guaranteed this matrix can be diagonalized by a similarity transformation. You are absolutely guaranteed. Yeah. What are the roots of this equation? 0 and 0, that is a double root, it is a repeated root. When I say it is a simple root I mean the root is not repeated, its multiplicity is 1. What about this matrix, 2 by 2 matrix? Can you diagonalize this by a similarity transformation, do you think? Well, you can easily see a dagger is going to have a 1 here and they do not commute with each other. These two do not commute, you write a dagger and you get one matrix, you write a dagger a you get another matrix, so they do not commute with each other. So it does not satisfy the sufficiency condition, but of course it may not be necessary. Now the question is, do you think this matrix can be diagonalized by a similarity transformation at all? What are the eigenvalues of this matrix? It is 0 and 0 because any triangular matrix in which everything below the principal diagonal is zeros, the eigenvalues are the diagonal elements themselves, and that is true for either upper or lower triangular matrices. So the eigenvalues of this matrix are 0 and 0. The characteristic function therefore must be of the form a squared is equal to 0. So the square of this matrix is the null matrix. That is also the minimal polynomial because the matrix itself is not 0 nor the identity matrix, so it cannot satisfy a linear equation. The next equation it satisfies a quadratic equation, but that must be the characteristic equation because it is a 2 by 2 matrix and that is a squared equal to 0 and the roots are not simple. So you are guaranteed this matrix cannot be diagonalized by a similarity transformation. but it does not stop you from finding the eigenvalues here and here. So the best you can do to any arbitrary matrix is not necessarily diagonalize it, but put it in what is called the Jordan normal form. So what you can do is to take this matrix, this huge matrix, and you can put it in blocks of different dimensionalities, etc. So you can have something here, you can have something here, you can have something here, and so on in diagonal form, and in each block corresponding to a given eigenvalue of some multiplicity you can bring it to the form lambda 1, lambda 1, lambda 1, a 1 here, a 1 here, 0, lambda 1, 1, etc., and then zeros everywhere. For instance, if this eigenvalue lambda 1 has multiplicity 3, it is possible finally to bring the matrix to a form where you have lambda 1s everywhere on the diagonal, an upper triangular matrix with 1s on this side here, and similarly for these other things. If it is a simple eigenvalue, then you just have a 1 by 1 matrix, a lambda 1 in that block. This is called the Jordan normal form, and that is the best you can do for an arbitrary matrix. You don't need to, may not be able to diagonalize it at all.